Okay, so now I can ask that question that I asked a little bit ago without meaning to, and that's all right. How is it that we get the temperature of a thing to change? And we've already, talked about it. We could put a thing in the bath of ice. We just need to go find a thing that is a different temperature and expose them to each other so that they can reach a thermal equilibrium. You know, ice is cold and flame is hot, and that's the deal. Direct heating with exposure to flame produces a temperature change. The question is how much, and that's what the rest of that's what this segment is about. And I think this is the only slide I need for this segment. Yep. Okay. Well, I'll come back to it in a second. But for now, how much exposure to flame do we need? How much? What do you want to call this? How much heating is proportional to how much change we want in our temperature? If we want something to get twice as hot, then we've got to heat twice as much. If we have twice as much stuff, if the mass of this substance that we're trying to change the temperature of is greater, we're going to need to do more heating. And you've probably already bumped into this equation before that we're going to call Q the quantity of heating, how much heating is going on. And we can relate that to the mass and the temperature if we talk about the heat capacity, and in this case, the specific heat capacity, because it depends what the object is. Is it water? Is it aluminum? What is it that we're trying to change the temperature of? Experimentally, we talk about quantities of heating. We could measure that exposure to the flame in hours if we wanted to, and just shake the units out later. How much heating did we do relative to how much temperature change we got, and what the mass is of the sample? And for each substance, we can graph that and find the constant proportionality. We can call that the specific heat capacity. How good is this specific material, at storing thermalness? We do some heating. Does its temperature increase a lot to account for that, or not a lot? And if delta T is generally small, then for the same heating, C must be generally bigger. This thing must generally be better at storing heating than another substance, because its temperature didn't change very much when we did this much heating. Cool. Now, mass is fine for solids, but if we've got a fluid, or especially a gas, something that's its mass isn't so much the issue, but the amount of it, right? It's how many molecules are there? Well, the mass of the sample is related to how many molecules there are, capital N, and the molecular mass. We could write it as the number of molecules. Let me just write it out. The number of molecules times the mass of each molecule. But that means we got to count how many molecules there are, and nobody wants to do that. We would rather count the number of, think back to chemistry, the number of moles, and multiply that by the mass per mole, or the molar mass. So in the textbook, you'll see the equation written m, n, lowercase n, number of moles. Molar mass, they use a capital M. Okay, so we could make that substitution up here. We could replace the mass of the sample with the number of moles and the molar mass times delta T. But now the specific heat capacity and the molar mass are both things that depend on which substance it is that we're talking about. So why keep track of two things when we could only keep track of one? Let's define, I'm gonna bring this down here. We'll use a different color so that we can. Let's define a molar heat capacity. And the interesting thing about the molar heat capacity, and now for this, I'm gonna have to share the screen again because this is cool. The molar heat capacities are oddly similar. The molar heat capacity for aluminum is 24 and a bit. For copper is 24 and a bit. For iron is 25, 26. For lead is 26. For silver is 25. Why are they all so similar if they're all supposed to be different substances? We were talking about a specific heat capacity relative to each thing, and their specific heat capacities are quite different, right? Aluminum is, like 3 times that of copper. Well, it's 9 times that of lead. Like these specific heat capacities are very different, but so are the molar masses. And I guess it's coming out in the wash, which is a very kind of accidental thing, I guess. We need to get to chapter 18 to figure out why. Okay. The last thing in this segment we've got to talk about is the fact that if we continue heating water, eventually it will boil and become water vapor, become steam. We still had to do heating in order to get that change of phase, right, to go from the liquid phase to the gas phase. But the temperature change, it doesn't change temperature. The boiling point of water is 100 degrees Celsius, or 373 Kelvin. So while the water is boiling, that is the temperature that it has. So as we continue heating, in order to get all the water to boil, it's not that this equation is no longer good because the temperature is no longer changing. So we need to find another way to keep track of the fact that we have a mass m of water, in this case, that we would like to cause to undergo a phase change. And the equation we'll use for that is the mass that we have, and capital L, which in this case is the latent heat of transformation, whether that's boiling or, well, the latent heat of fusion for melting or freezing, the latent heat of vaporization for evaporation or condensation. It's up to us to keep track of whether this is a heating that we did with a hot thing, a flame like that, or whether it's heating that we did by exposing the thing to a cold environment, such that we're heating in reverse, right? We're heating the cold thing with our sample as opposed to heating our sample with a hot thing. So it's up to us to keep track of whether that's positive or negative, and up to us to keep track of which phase change we're talking about. And I didn't even include the table. There's a table in the book of latent heats of phase change, vaporization, and fusion. Okay, and then there's 3 or 4 worked examples in this section of the text that I strongly encourage you to take a look at before you, or during your work on the Mastering Physics for chapter 17. Speaking of which, right now, chapter 17, 18, 19, and 20 are all bunched together at the end. I would not leave them until the end. We're going to finish chapter 17 today, and I would start working this week on chapter 17. Okay. I'll leave the examples to you, though. If you have questions, of course, send me an email, hop into the class time Zoom meetings, and we'll get it talked about. Okay. One more segment left, and then we're done with chapter 17.